Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of NPTEL course on thermal physics. Now, in the last lecture, we have discussed about mean free path in details and also the terms like collision probability, both in terms of energy, time and distance. And we have established a relation between these two parameters, that is tau, that is the collision frequency in time, and lambda, which is the mean free path, which is in distance. So, basically lambda gives you the average distance over the entire gas assembly in terms of the average distance of a particle can travel inside this gas assembly without suffering a collision. Similarly, the mean free time lambda is the average time between two successive collisions. And strictly speaking, like the Maxwell's velocity speed distribution function, they also have a distribution. Okay. So, these are the average values of what we are average value what we are talking about. So, if for example, if the in a Maxwell distribution speed distribution case, we have seen that the maximum numbers of molecules stay in the vicinity of the top of the distribution curve, that is close to the mean velocity or close to the most probable velocity, mean speed or most probable speed. But in principle, there are molecules or there are gas particles which have 0 velocity, and there are gas particles which has nearly infinite velocity, nearly 0 and nearly infinite velocity. So, these are possible. Similarly, the mean free path and mean free time or the collision frequency, whatever inverse of collision frequency, whatever we call it, these are actually the average over the entire assembly. Now, if we go back to the mathematical derivation we did in the last class and we see, we look back into this relation, we see we have derived two relations. Tau is equal to 1 by n sigma c, and lambda is equal to c bar divided by n sigma c. Now, n is the number density, n is do not confuse it with the moles, n is the number density. So, n is simply equal to n is simply equal to capital N by V, that is the total number of molecules in the gas assembly divided by total volume, and sigma and sigma is the collision cross section. C bar is the average mean velocity from the Maxwellian distribution, and we know that C bar will be equal to root 8 kT by pi m, right. So, this is what we have already derived. I am not going into the detailed discussion of these terms once again, but what is important that there are two more parameters in this expression. One is this C, which is marked in red, and one is this sigma, which is the collision cross section. Now, the question is, what are the values of sigma and what are the values of this C, which I should once again write in red, because this is more or less the convention I have followed. Okay. So, what is this C and what is this sigma? Now, sigma, as we know, this is the collision cross section, and we very soon we will start with determining an expression for sigma in terms of the molecular parameter. Question still remains, what is C? C is the speed which with which our molecule moving on an average. So, the okay. So, let us first discuss about sigma, okay, and we try to determine an expression for sigma, then we will come back to C, right. So, in order to determine sigma, let us focus on this following picture. Let us assume there is a gas particle, let us name it gas particle 1, which is moving with an uniform speed or in this particular direction, okay. And there is the second particle, we call it the particle 2, it has a radius r2, whereas the first one has a radius r1, and this is somewhere in the space. Now, look at this picture carefully. So, this dotted line actually that marks a cylinder that is traced out in space by this particular molecule 1. And if and only if there is a overlap of this cylinder, which is marked by these dotted lines, and with the second molecule there is a collision, right. So, we have drawn the second molecule in two different positions, position 1, position A and position B, right. In position 1 or position A, the second molecule lies outside this cylinder of influence and there is no collision. And in position B, in case B, or rather I should say case A and case B, in case B the second molecule somehow the volume of that molecule has an overlap with the cylinder of influence of the molecule 1. So, in that case there will be a collision. Now, mathematically speaking, we have this is the Hart sphere approximation, where we assume that during the collision the volume of the cylinder or volume of the gas molecule does not change. Now, in reality what happens is we have one molecule here and the second molecule coming in, they collide, and once they collide there is a shrinking in volume. So, basically it is a elastic deformation, because molecules are finally, I mean, although we look at it as if they are Hart sphere, but they are not, they have electron cloud in the outermost shell, and the electrons they interact and they, I mean, I should not say that they contract like what happens to molecules in a collision between two tennis balls, for example, they contract. I am not saying they do that, but of course there are some sort of interaction, okay, and there is some atomic deformation or molecular deformation present, and we are ignoring that in this particular Hart sphere model. We are totally ignoring that. So, all we care about is in position A there is a no collision, in position B there is collision. Now, if the respective radiuses are r1 and r2 of molecule type 1 and molecule type 2, then we can write in position A, or in position A the center to center distance d is greater than, oops, I should make it r1 and r2, my fault, yeah, so it should be, just a minute. Yeah, R1 and R2, right. When D is greater than R1 and R2, there is no contact between them. And in position 2, let us go back, D is equal to the center to center distance, D being the center to center distance. So, center to center distance at the point of collision, when this molecule will come to this particular position, okay, or rather this molecule will come to this particular position, it will be something like this, yeah, and the center to center distance becomes less. Of course, it cannot be less because these are Hart sphere. So, what happens is it comes to contact and then it deviates in another direction. So, that is exactly what is written here, that for R1 D is equal to R1 plus R2, okay, there is a collision. So, in Hart sphere approximation, the collision cross section is defined by pi d square. So, basically, sorry, so this is now let us assume that these molecules are inside the same gas assembly. So, they are basically the same molecule, just for illustrative purpose I have put R1 and R2, but they have equal radius. So, what happens is when there is a, let me try to draw this quickly so that I give you a better understanding. Yeah. So, I have one molecule. My drawing is never that great, so you have to bear with it. Yeah. So, you have one molecule and the second molecule can come in contact with the first one if and only if the center to center distance is d, which is 2r. Now try to assume this. We draw a circle of radius d, not radius r but radius d. It is a hypothetical circle. Okay. So, any molecule that comes within this circle, the center of that molecule, if that comes within this circle, there is a collision. So, this basically the effective cross section of this molecule 1. So, let us call it molecule 1. Okay. So, this is the shaded area. I will just mark it with blue, maybe, I do not know. Yeah, this shaded area is actually the effective cross section of this molecule as it travels through space. So, this the area that area is given by A, or rather we will call it the A cross section is equal to pi d square. Okay. I hope this makes sense. Now, let us go back. Yeah, so we just written this expression here. Probably I will make some changes in this text because the text sometimes gets a bit confusing here maybe. So, I will make slight changes and then, but anyway, from this picture itself you get a better feel for it. Okay. So, now we know that this is nothing but sigma. So, basically we get sigma equal to pi d square, right. So, out of two parameters of interest, one was sigma and another was c. So, we have got an expression for sigma here. Now, next up is c. So, you would like to see what are the possible values or what are the possibilities in which way we can find c. Okay. So, the first approximation is 0th order. In the 0th order approximation, you see that all molecules are frozen. So, that is exactly how we first described or determined the expression for lambda. So, we have assumed that all the molecules are frozen and only one molecule, the so called tagged particle, is moving. And this is exactly the same way we have computed this one also, the collision cross section also. We have assumed that these molecules are more or less are frozen and this is the only one that is moving, just for the better understanding. But in principle, even if all the molecules are moving, this picture does not change. If and only if the center to center distance becomes I mean the center to center distance equals to this 2r, only then there is a collision. So, the minimum distance that the collision cross section remains pi d square. But once again, let us go back to the 0th order approximation when we assume that all the molecules are frozen and our tagged particle is the only one that is moving through space. Now, in this case, and that one is moving with the average speed c, okay, and bluntly we just put c is equal to c average or c mean, and then going back to this expression, what happens? This c bar over here and c bar over here cancels out and we have lambda is equal to 1 by pi d. Also, we can write an expression for tau. Tau will be 1 by n sigma C bar, right? We can do that. Now, this one gives you an idea. I mean, of course, it gives you an idea, but this is an oversimplification by all means. We cannot make all molecules frozen, and we cannot assume that even if there is only one molecule moving, that is moving with the average speed. So, it is a vast oversimplification of the situation, but anyway it gives us an idea of what should be the what is an approximate, or what could be an approximate expression for lambda. Now, next comes the first order approximation, and this was given by Clausius, none other than the great Clausius. So, he assumed, okay, so let us make all the molecules move, and for simplicity we just say that all of them move in different directions. There is no restriction that they have to move in one particular direction, but they move with the average speed c bar, that is the mean speed of the gas assembly. So, he did not reject the idea of speed distribution. I mean, so basically he did not assume any distribution of the speed, but he has assumed uniform speed but different velocity of the gas assembly. Now, then the calculation becomes kind of simple. Okay, let us see, right. So, the calculation, what happens is, what we have to do is, we have to determine the relative velocity between two particles. If two particles are moving in two different directions, they have a relative velocity, and the c in the expression for lambda, what we have to put is that relative velocity. Now, let us consider this situation here. Let us say we have two molecules both moving with the same speed c, but in different direction. So, what we have to do is, we have to, in order to find out the relative velocity, we have to come back to this basic vector diagram. We have put one velocity OA here, the other velocity OB is in this arm, and the angle between them is theta, simple. So, the relative velocity CR is nothing but this vector AB, and from vector diagram we immediately see that AB is equal to OB minus OA, right. Oh, sorry, there should be a minus sign here, my mistake, OB minus OA. Now, if written in terms of proper vector components, the magnitude of CR is, so I probably should elaborate a little more on this so that you understand it better. Yeah, so I have one vector, I have the second vector, same magnitude but different direction, and the third vector, okay, the third vector is just connecting these two. Yeah, so basically O A B, so OA plus AB is equal to OB, right. So, this is the simple vector equation. So, AB is nothing but OB minus OA, and OB mod is equal to OA mod is equal to C bar, and this is CR. So, this is C bar, this is C bar, and this is CR. So, from this equation we see that AB mod is nothing but OB square plus OA square, and the angle is theta, minus 2 OA OB cos theta, fantastic, right. And this is nothing but, so basically CR is equal to C bar square, or 2 C bar square, because this is C bar, this is C bar, minus 2 C bar square, sorry, this is cos square theta, yeah, right, yeah. So, simplifying, you see, you can take 2 C bar square common from these two terms, and then you can take it out of the root, putting root 2 c bar is equal to 1 plus cos square theta whole to the power half. Now, we write cos square theta using this trigonometric identity as cos square theta is equal to 1 minus 2 sin square theta by 2, and very simply we have c bar or CR magnitude is equal to 2 c bar sin theta by 2, 2 c bar sin theta by 2. Now, this is for only one specific value of theta, and Clausius assumed that gas molecules are moving in all possible directions relative to each other. So, what we have to do is in the simplified, even in the simplified assumption, we have to find out the average value of CR, which will be averaging over all the possible theta values. And once we do that, so CR average is basically what we have to do is we have to do it for this entire 4 pi solid angle. Why 4 pi solid angle? Because I will just try to make you understand here. So, let us say one molecule is our reference molecule is sitting at the center. So, the other molecule can make or let us say, okay, so let us say this one has a velocity component in this direction. Okay. Now, what are the possibilities of other different directions we have? We can have anywhere on this sphere actually. So, the other velocity, second velocity the second molecule can be anywhere on this sphere. And what is the total area of this sphere in terms of solid angle? This is 4 pi. So, what we have to do is we have to average it over this entire 4 pi solid angle divided by 4 pi. So, the element, and please remember that the radius is fixed, radius of this sphere is fixed. So, any element on this will be r sin theta d theta d phi, and r is fixed, and once we try to compute the solid angle due to this particular area, so it will be r sin theta d theta d phi, right. So, this will be d omega is equal to a by 4 pi by a. It will be a over, so this is dA, the area here, dA over r, this should be r square, dA over r square, right. Okay. So, this is nothing but sin theta d theta d phi. Okay. So, this is exactly what we are doing. We are integrating over d phi and integrating over sin theta d theta multiplied by 2 CR sin theta by 2 over 0 to pi, right. So, that is the range of theta. I hope you understand that, but let me tell you anyway, theta can vary between this angle which is 0 to this angle which is 180 degree, which is pi, and phi can have altogether 2 pi or full circle turn radius, full circle value. So, we have 2 pi coming from here, 2 coming from here. So, 4 pi is in the denominator, both all nicely cancels out, leaving behind CR 0 to pi sin theta by 2 d theta. Further simplification is done by writing sin theta is equal to 2 sin theta by 2 cos theta by 2, which is 2 CR 0 to pi sin square theta by 2 cos theta by 2 d theta. And by a very simple substitution, we get this integration as 4 times 0 to, or 2 times 0 to 1 x square dx, which is finally gives us 4/3 CR, right. CR, 4/3 C bar I should write, not CR, because CR is this one, these are all C bar, my mistake. right. So, basically CR average, yeah, so this will be CR average, this is C bar, so from here this is C bar, C bar, C bar, here also C bar and 4/3 C bar, right. So, now this is nothing but our C which we are looking for. So, going back to this expression, we will have to simply substitute. So, we go back to this expression once again, we have to simply substitute C bar C with 4/3 C bar, and the final expression that we get is lambda is equal to 3/4 n sigma, which is 0.75 n sigma, which is a 25% correction over the 0th order approximation, right. Now, the next one is the second order approximation, which is a very involved discussion, where it is by Maxwell actually. Now, Maxwell assumed that all molecules move with different speed and velocity. When I say different speed and velocity, that means different magnitude and direction. So, everyone is going random in a random manner, just the way we think of a Maxwell's speed distribution function. So, basically all the molecules have different speed and basically different velocity, because they are colliding with each other, moving in different directions. And then the gas assembly also follows the Maxwell speed distribution function, speed distribution law. And we are not going into this detailed calculation. These are worked out in the book. If you all the textbooks I have mentioned, if you are interested, you can go through it. It's almost like in the textbooks itself. It's a 2 to 3 page calculation. Not going through it, but finally we get an expression which is lambda is equal to 1 by root 2 pi n sigma, which is 0.707 n sigma. Now, with a very simplistic model and a simple averaging, we can get 0.75, and with a much more complicated calculation, much more complicated involved mathematics, we get 0.707, and the ratio of these two is 94%, is 0.94. So, the first order approximation is almost 94% accurate as compared to the more more detailed second order approximation. Now, it so happens that although we do not want to go into the details of this derivation, there is a very simple way of deriving the exact same expression, and that was by P's. So, it is an easy alternative. We get the same expression, and but again it might look oversimplified to you. I also think that way, but anyway I thought I will discuss it. So, what Pease did was he essentially treated the molecular impact as a two body problem. Now, in a two body problem we have two molecules M1 and M2 with radius d1 and d2. So, the d between them or diameter d1 and d2. So, the d will be the impact distance, d will be d1 plus d2 divided by 2, and because it is a two body problem, the effective mass has to come into picture. So, this system will have an effective mass mu, which is given by m1 m2 divided by m1 plus m2. So, for this two body case, the mean speed of the gas assembly will be simply reduced to root over 8 kT by pi mu instead of pi m. Now, once again, if we are talking about the uniform gas assembly where there is there is only one type of gas molecule present, we simply have m1 is equal to m2 and d1 is equal to d2 is equal to d, then mu becomes m by 2. Okay. And CD, that is the two body diameter, so this is the two body mean speed of the system. It just becomes root over m kT by pi m, but because m is replaced by m by 2, there is an extra factor of root 2 comes out here, which is root 2 C bar. C bar is the mean speed of the Maxwell distribution, and this very simple treatment gives you the exact same expression of tau and lambda which we get from the Maxwell's more detailed, more elaborate calculation, and that is root over 1 by 2 n sigma. So, now we see that what are the actual or what are the detailed physical way of dealing with these problems. We have also come up with proper expressions for the mean free path lambda and the mean free time tau. Of course, they are related by the simple relation that lambda is equal to tau times c bar being the mean speed of the Maxwell's speed distribution function. Now, it comes to measurement. How do we measure that experimentally? Because as I keep repeating the same thing over and over again, unless and until you can measure something, that theory is not proved beyond doubt. So, mean free path and all, everything is good, but how to measure it experimentally, and basically how to measure it experimentally. The next class we will have a discussion on that, but let me tell you a very quick let me quickly tell you that there is a very simple way of writing this expression for lambda and tau in terms of the measurable parameters, that is pressure, volume and temperature. Remember, ideal gas, especially for an ideal gas, the ideal gas equation is PV is equal to N kBT. Okay, so this is the familiar form, PV is equal to N kBT. All I did is I just removed this V from here and took it into the denominator. Then N by V is equal to small n in this expression, in this expression and this expression. So, P is equal to N kBT. So, all we have to do is we have to substitute for N with P by kBT, and we write lambda is equal to kBT divided by root 2 P pi d square. If we have an idea of the molecular distribution or molecular diameter, and if we know the temperature and the pressure of the gas assembly, then we can very easily measure the mean free path. And once we know mean free path, also we can know mean free time, because this is just a factor of c bar between them, and c bar is the mean speed, which is totally determined once again from these parameters, right? Because if you recall, c bar is nothing but root 8 kT by pi m. If we already know kT, we are good, and all we need to know is m. So, all we need is the temperature of the gas assembly, the pressure of the gas assembly, the diameter of the molecule and the mass of the molecule in order to estimate the value of lambda and tau. Okay, so that is where we stop today. In the next lecture, we will be talking about how to determine the parameter lambda experimentally in a proper experiment, how do we measure that, and we will also solve some problems. Thank you.